Hello, everyone. Welcome to the 12th webinar in the Joint Tran-SET webinar series, which will cover different topics related to corrosion management system of transportation infrastructure for long-term durability, reinforced concrete structures. So this webinar is organized by Tran-SET in collaboration with Texas A&M. So yesterday was part one of this webinar, and we had 3 related amazing presentations. So today is part 2, and we will have 3 more experts presenting about this topic. We will have 3 15 to 20-minute presentations. So first, Michael Stroya will provide a review of recent performance testing, corrosion mechanism, and applications of continuously galvanized reinforcement. After that, Anthony Del Percio will provide a mechanistic discussion of the mechanistic performance of dual-coated steel reinforcement epoxy over continuously galvanized rebars. And finally, Dr. Salim Vaza will provide a presentation about the mechanistic performance of continuously galvanized high-strength corrosion-resistant Chrome X reinforcement. So we will save our questions until the end of the 3 presentations for a 15-minute group Q&A. You can type your questions anytime throughout the session. Now I will introduce our first presenter, Michael Stroya. So Mr. Stroya is responsible for expanding galvanized products and technology in steel and concrete reinforcing markets. With more than 25 years of experience in the galvanizing and corrosion control industry, he has specialized in galvanized coatings, and he has been involved in the development and code acceptance of galvanized steel products nationally. Mr. Stroya holds a degree from Kent State University and contributes to ASTM, CRSI, NACE, TRB, and ACI committees. He is currently involved in recent works at Texas A&M Center for Infrastructure and its comprehensive corrosion performance study for materials used for reinforced concrete system. Michael, I will turn it over to you now.
Okay, how are we doing? You see the screen?
Yeah, so we can see your current screen and with your next slide and your comments.
Oh, you're seeing the notes. Okay, let me try this again.
Yeah, try it. Yeah, take your time. So while Mr. Stroya is trying to share his screen, I would like to remind everyone that after the webinar, we will have, yeah, Mr. Stroya, it's clear now, only your current screen. But let me first remind the attendees that we, after the webinar, within 2 days, we will upload the recording of this webinar as well as the presentation slides on our website and or on our YouTube channel. So if you have a problem with accessing these files, just shoot me an email at transit@lsu.edu. And again, I will add the link for our website in the chat box as long as our email. So Michael, yeah, we can see your screen, so you can start your presentation.
Okay, thank you, Dr. Musa, and wanted to extend my thanks to Dr. Hassan, Dr. Musa, and Dr. Castaneda for allowing us to be a part of part 2 of the joint Tran-SET webinar series with Texas A&M. I do want to preface by saying may intermingle some words with CMC's trademark word GalvaBar or continuously galvanized rebar. I'm referencing A1054 standard, and also with the ASTM A767 standard, I may use the word batch just in case to give you some clarity there. But I wanted to start off and talk about
Michael, I'm sorry for interrupting you, but I think there's a problem with the audio. So I think when you started your presentation, there is a problem with the audio. Can you just speak again? Because I think maybe the connection is poor or something. We got
okay. Can you still hear me?
Yeah, now it's great. Yeah.
Okay. Well, I'll back up and say that, you know, extend my thanks to you and Dr. Castaneda and Dr. Hassan I'm happy to be here today, and if you didn't hear this already, I want to preface by saying if I say CMC GalvaBar, I'm referencing the A1094 standard, or if I say continuously galvanized rebar, I'm also referencing the A1094 standard. And with the ASTM A767 product, I may intermingle the word batch, just so we're all on the same point of reference. The key points for the presentation today, galvanized rebar is the lowest cost corrosion resistant rebar for the life of your concrete reinforced structures. But today I'll discuss the differences between the two standards, A1094 and A767. Both are fantastic products, widely recognized and used throughout North America and the world. But again, today I want you to know that there's key differentiators between the two products. And there's some demonstrations that I'll provide later that show A1094 has better testing data. A1094 has an innovative control process with quality at every step. And A1094 has a superior supply chain for delivery of product. Also, at the end of the presentation, you'll recognize that A1094 is the lowest cost corrosion resistant rebar for owners over the life of your infrastructure. At a minimum today, I'd like you to recognize that ASTM A1094 is and should be an equal footing to 767 as a direct substitute. There are two competing products, both last a long time, but you'll see some clear advantages coming up. And for those not using either 767 or A1094, this would be a great opportunity for you to look at corrosion resistant rebar for the life of, for the lowest cost over the life of your structures. Moving on to commercial metals and who we are. In July of 2020, Commercial Metals Company purchased the assets of GalvaBar. Commercial Metals Company and its subsidiaries manufacture, recycle, and market steel and metal related products, materials, and services through a network of facilities, including 7 electric arc furnace mini mills, 2 EAF micro mills, 2 re-rolling mills, and steel fabrication and processing plants, along with construction related product warehouses and metal recycling facilities throughout the United States and Poland. CMC is the largest rebar producer and fabricator in the United States. And along with GalvaBar, the continuously galvanized rebar, we offer epoxy coated rebar and high strength Chromex corrosion resistant rebars. Talking about what continuous galvanizing or A1094 standard is, it's galvanized reinforcement, and the product is an automated process, an automated process that built around quality and consistency with the end users in mind. A1094 addresses the last mile issues of quality, availability, logistics, durability, and service often found in other corrosion resistant rebar products. A1094 easily bends like uncoated or black bar, and you can design it just like uncoated black bar. Some of you heard Dr. Yeoman's and Dr. Castaneda's presentations yesterday, and I'll highlight some of those in the upcoming events. But we'll be addressing some of these key points listed here of the continuous galvanizing process yielding consistent formable coating, fabricating prior to processing with no special equipment, and a thicker pure zinc coating that increases the corrosion initiation threshold, as well as an inventory product that reduces competitive costs with those last mile advantages. Specifications for galvanized reinforcement are, as you see below. All these standards allow for a coating of A615, A706, and A996 concrete reinforcing bar standards. A1094 also allows an additional substrate of A1035, high strength corrosion resistant rebar, and you'll see that presentation later today. And A1055 has 2 types of zinc protecting as a substrate, metallizing, and our 1094 product is type 2. A767 is the standard for zinc coated steel bars and concrete, often refers to batch coating. A little bit about fabrication. One of the key differentiators in the products of A1094 and A767 is the ability to fabricate after processing. You can see different types of machinery, different thicknesses of bars, And the same great coating don't have any impact on whether it cracks or peels, because there's no cracking or peeling once it's bent, and there's no repairs needed after bending, allowing us to use the most efficient machinery out there and all kinds of bars from number 3 to number 11 and up to over 60 feet in length. The process and how it's made, I'll go over 2 steps here. The next one's a video. Hopefully that'll come through. And as you can see, the diagram here is for an individual lane. We use multiple lanes, but we start off with mill certs and mill tags and that are identified and removed for post-galvanizing package and traceability and quality control steps. So once we remove those, we take the bundles of rebar and we advance them in queues and from size 3 to up to 11 and up to 60 plus feet. And we align those for processing. And the first step here is that the uncoated bars pass through individual lanes and advance to their abrasive blasting, where bars are clean, removing and mill scale, and they're prepared for flexing. In all steps of the way, again, they're in individual lanes, and whether the processing step is coating or is preparing at 360 degrees around the surface. So the next step after abrasive blasting, again, is flexing, where the bars are advancing after that into an induction heater. The induction heating temperature raises the temperature quickly, instantly drying the flux and preparing it for the galvanizing process, somewhere close to 400 degrees. Once it enters into the galvanizing process, it occurs very rapidly, passing through, again, in individual lanes through the zinc trough, covering, again, 360 degrees evenly around the bar without sticking together or any touch marks. After the galvanizing process, air knives define the galvanizing rebar, removing any sharp or injurious spikes or heavy drain lines. And then the next step would be the rebars are cooled and passivated per our ASTM A1054 specifications to prevent any potential reaction in concrete. And finally, bars are bundled back into the original received bundles with original tags, our quality inspection tags, and further electronically logged for additional quality assurance steps and available for either shipment or inspection. Next is a video here that will go through those steps that I described. Oh, we'll go back. There we go. As you can see, bars are individually controlled and enter into the abrasive blasting, which removes the oxide scales and mill scales that are often on the bar. Individual lanes advance, again, into the pre-flex station, where the flexing prepares it for the galvanizing process. Induction heating dries the flux and prepares it for the galvanizing process, and then moves rapidly into the galvanizing process, where a reaction happens almost immediately. In a matter of seconds, it comes through the other end, is defined by an air knife. So there's minimal dwell time in this process. After the air knife defines the bar, it goes into post-treatment after it's cooled. Passivation treatment, preventing any potential reaction in concrete. Bars are then inspected for quality and prepared for bundling and either additional inspection or shipment. It's a relatively quick process and very labor-free. Not many people on our line, so it's more quality control than anything. Where A1094 product is being used, these are different types and different installations we've done across the country and even in Bermuda. And you see in the top left, the precast structures or even shotcrete process or projects that we're looking at showcase the durability of the product. For precast structures, we've done some nice projects in Vermont, in the Northeast states, and all over the country, really. But shotcrete's an exciting opportunity too that showcases the extreme durability of the coating, where they're using it for rehabilitations or strengthening projects. Shotcrete goes on at about 6,000 PSI They're even looking at some dam applications where they're rehabilitating these projects. When they shotcrete with a high pressure, our coating still holds up to it without any problems. Bridge decks are our largest market right now, with opportunities for owners to see reduction in cracking, long service, and demonstrates the field durability for these jobs in high chloride exposed environments. The picture you see there, which we'll talk about a little bit later, is for a Buffalo Creek Bridge in Iowa. But we also have numerous installations across the states, such as Rhode Island, Vermont, Ohio, Indiana, Missouri, Kentucky, and planned projects upcoming in Texas, Colorado, New Mexico, South Carolina, and New Jersey, among others. Transportation systems are some recent projects that we've been involved in with structures that are state-related, but other than decks. This example here is an Ohio DOT installation, but we've also done projects for SEPTA, which is the Southeast Pennsylvania Transportation Authority, as well as projects upcoming Maryland and Massachusetts in planning. Coastal and marine environments are also an opportunity for us to showcase our product in high chloride environments. This particular project up in the right-hand corner there is a coastal structure that's right on the beachfront, utilizing our GalvaBar or continuously galvanized rebar product right on the ocean front in a high chloride environment. Waste treatment products, wastewater treatment plants are also an excellent product where you often have areas that aren't accessible for repairs. You see an example there. Parking garages and balconies, particularly in the chloride heavy states, Florida and the Gulf Coast. We've seen many of these projects. They're mostly private, but these are commercial, but these owners realize the return on the small initial cost increase over uncoated or black bar. And then lastly, we do a lot of work in foundations, whether it's a U-Haul or other projects that have foundations in contact with soil or seawater. We're seeing a lot of people utilizing cathodic protection in the last mile of additional extension of life. But here you can use cathodic protection of galvanized rebar up front and much less costly than cathodic protection, and save your structure in the front instead of at the end. Here's a couple case studies that I referenced earlier. This is the Buffalo Creek, Iowa Bridge, designed for a 100-year life with galvanized beams, pilings, and continuously galvanized rebar. Buffalo Creek's Brian Kylever was excited to use our product for his project at Buffalo Creek because it helped him with his timeline. The A1094 availability and supply chain here shipped from distribution and helped with achieving a short construction time span before the winter's onset. They don't have a lot of time to work in projects at the end of the year. And supply of the A767 galvanized rebar from the local suppliers would have missed the timeline and put construction into the following year, but they're able to use our bar and save the timeline and open up early in the next spring. Another opportunity for GalvaBar to save the day was at the U.S. Army Corps of Engineers in a paving project at Fort Hood. Originally specified again for A767, 1094 was substituted as an equal to fixed timeline constraints from local suppliers of A767 at the beginning of the job. The substitution allowed for the contractor and fabricator to make up for lost time in a very rigorous construction schedule at a military installation at Fort Hood. And we'll be also working on some future projects with them. Now on to some research done at Texas A&M Center for Infrastructure Reliability that's been in progress and will be ongoing. Over the last couple of years, Texas A&M's been conducting mechanistic testing of different types of rebar for reinforced concrete systems. And I'd like to thank Dr. Homero Castaneda and his team for all the work they've done, and they will do. The rebar types can be broken down to compare our galvanized rebar types of A767 and A1084, which you'll see in the upcoming slides, and also the upcoming presentations of A1055 dual-coated epoxy over 1094 and the A1094 as a coating over top of high-strength corrosion-resistant Chromex. On to the presentation. And some of you saw this yesterday if you joined us. It was presented by both Dr. Yeomans and Dr. Castaneda, where you see your typical initiation propagation concrete corrosion model on the left. And on the right diagram is here where the model for galvanized rebar and its protection are recognized. ASTM A767 and A1094 standards both have durable zinc coatings with a metallurgically bonded zinc coating structure that provides a barrier and sacrificial protection while improving bond strength. Now, the differences in between the left and the right are that zinc corrosion products of any kind are much less voluminous than iron corrosion products. But we're recognizing that pure zinc corrosion products are less volume than the zinc iron corrosion products, which will cause stress eventually. A1094 has less expansive, less voluminous zinc corrosion products, and it's a more homogeneous coating structure, which is more zinc and much less iron, which results in efficient use of zinc and improvements in protection that we'll demonstrate here. Using some NACE testing guidelines for open circuit potential, this short window test with 30 days was establishing a passive condition, and then we establish a 90% risk of corrosion line. Anything above that line is not providing any protection. And then we establish a cathodic protection limit. Anything more negative than this cathodic protection limit is shown to be providing cathodic protection. And the more negative, the better. It's a short window test, but it demonstrates that both coatings, A767 and A1094, are providing adequate cathodic protection in an open circuit potential test. And again, the more negative, the better, which A1094 is slightly better here than 767. Now on to electrochemical impedance spectroscopy, EIS. That's why we call it EIS, because it's hard to pronounce. But in any case, EIS in these next couple tests will show the progression of the coating and resistance over the first 30 days of comparing A767 and A1084. Dr. Castaneda explained this very well yesterday and went into some extended details of the importance of this testing. But what you're seeing is an evolution of the coating, or how the coating dissolves, how corrosion products are formed, and in this case, zinc corrosion products, and overall how homogeneous the coating structure is. So on the right side, you see a phase angle, and you see where the A767 samples end up. And as time progresses, the resistance or the protection goes down for A767 much faster. And day 30 resistance is relatively low that you see on the left-hand side. Comparing that to EIS results for A1094, you see the same EIS testing here, but as time progresses, you see that A1094 is more resistant than A767 and has developed a more homogeneous coating structure. As you can see, after the 30 days, the resistance level is higher than A767 and A1094, meaning that there's a better resistance as a coating, regardless of coating thickness. Our next test is a demonstration for continuous immersion for A767. On the left side, you see impedance or resistance scale measured in ohms per centimeter squared on the left. And this data for the next two slides is well over a year. I think we're up to 400 days. This particular example is 342 days, I think exactly. But we're showing resistance compared to A615 bar conducted in the same time period. And you see the on the left, on the bottom there, you have A615 pointing out the point where the passive is protecting and then breaking down in the final in the end. And then you see the dotted lines in the blue where the galvanized A767 product starts to corrode, and the zinc corrosion products react and protect it. Looking at it closely over a year, it's a marked improvement over top of A615 at 3,600 ohms per centimeter squared. Comparing that directly to A1094, you can see the protection method on the bottom again for A1094 for the same period of time as 767. However, the resistance ends up much higher. The same scales apply in the bottom, and as you can see in a close-up, A1094 is over 2.5 times improved resistance over 767 at 9,600 ohms per centimeter square. You can also convert this data to show it as a corrosion rate, which we'll be doing in an upcoming paper. But what this demonstrates is that thickness doesn't matter again. Quality and consistency of the coating structure and the makeup of the coating structure do. This is why you'll have the lowest life cycle cost based on this higher corrosion rate and the benefit of a superior supply chain, which we will demonstrate. So a quick summary here for Texas A&M research, which again is ongoing, but we're showing improvements for A1094 compared to A767 and all the tests conducted so far. There's less expansive product or corrosion byproducts, zinc corrosion products, which will show to relieve stress, allowing less corroids to reach the rebar. We're showing a slower corrosion rate and major improvements in resistance to corrosion, which is very important. Again, a paper will be released that has thorough details of the mechanistic performance of both rebars, including concrete testing that's underway and chloride threshold testing that's underway. Now I want to explain the difference in the two coatings as you see in a photomicrograph. What you see on the left is an ideal coating structure for galvanized A67 rebar. On the coating on the right is the same product that can develop a thicker iron-rich zinc intermetallic. To compare the differences a little bit better, you can see on the left here we have the A1094 product and on the right an A767 product and what happens between the two. When you look at the performance, quality, and consistency of the pure zinc coating, that's the key and not the total thickness. So what I like to highlight here is that, we have a pure zinc coating versus the batch process. The pure zinc layer does the heavy lifting for protection in either coating. And as Dr. Yeomans demonstrated more, A1094 has a thicker pure zinc coating than A767. Zinc iron can be more expanded. You're seeing in a reactive coating, you're seeing a pure zinc layer at the top and the ADA layer that's relatively thin in a reactive steel. Zinc iron is also more expansive than pure zinc and will assist in cracking eventually, allowing more chlorides in quicker. You're looking at a zinc iron that's also brittle for field fabricating and can grow to the surface. It's not uncommon for A767 to develop a heavy brittle coating with zinc iron intermetallic because the process is chemistry reliant. Where the A1094 process will develop a consistent pure coating above standard specified minimums regardless of steel chemistry without any fear of hydrogen or strain age embrittlement. Talking about some other available research comparing the two standards, we've seen Dr. Castaneda's Texas A&M research that I just presented. We also demonstrated, and you heard that from Dr. Yeomans yesterday, that A1094 product is a thicker pure zinc layer over 767, and he's an excellent galvanized rebar chloride 3 researcher. In the University of Akron, Ohio DOT federally funded study, you see a larger reduction in bridge DAC cracking and improvements in corrosion. And also, an interim report was available and will be finishing the second year of an equal or better performance for corrosion resistance and the University of Kansas for Matt O'Reilly. So these are other excellent examples of a comparison between A1094 and A767. Talking about our procurement chain, the utilization of our supply chain is key. We have steel mills, fabricators, distributors, utilizing inventory or supplying material available to toll coat at our plants. We have the largest supply chain of any existing corrosion resistant reinforcement. Processing prior to fabrication is a key. You don't need any special equipment needed to fabricate, and the most efficient machinery is can be utilized without any special rolling or equipment. We can stage from anywhere from number 3 to number 11 in the different grades of material. The common sizes are typically from 4 to 8 and grade 6, 15, but as CMC or any other plant, they can bring in material of any grade and allow for staged inventory across the country. And again, up to 20 to 60 feet. This allows for a very consistent flow of material across the country from coast to coast, north to south. We can go anywhere. There's no additional handling, and this is another great opportunity here, which means there's a seamless supply of rebar out there. You don't have to double handle material, get back in line to get your product galvanized again. There's no lost or missing pieces or lost or missing tags with our product because the fab shops own this material or the steel mills own this material. Overall, what you get is an improved customer satisfaction. So really wrapping it up here, you know, I do want to say that ASTM A767 is a good product, but we here believe that ASTM A1054 is a great product. And today, I think I've demonstrated that A1094 offers improvements over 767 in both corrosion and supply chain for sure. And so we're asking DOTs and the architect and engineering community to specify A1094. And if you're specifying A767, A1094 should be a direct substitute with improvements in corrosion resistance, quality, and availability. Our innovative process allows for consistent quality, so it won't let you down. And with our supply chain improvements, this goes right in with that. A1084 will be your lowest cost corrosion resistant rebar of the life of your structure. And we're ready to assist you with live fabrication demos or even plant tours as necessary when things get back to normal here. And we'd also love to help with developing your specifications for your state or municipality. And most of all, we'd love to assist in demonstration projects, bridges for opportunities within your region or state at competitively priced products. So with that, wrapping up here, I do want to say that I want to thank everyone for helping put this together. And privately, you can reach us at GalvaBar at CMC or look at further information on our cmc.com GalvaBar website. Thank you, Momin.
Perfect. Thank you very much, Michael. That was very informative and interesting. So let me share my screen. Okay, thank you again, Michael. So now I will introduce our second speaker, Anthony Del Percio. Anthony is responsible for expanding epoxy coating products and technology in steel and concrete reinforcing markets. With more than 31 years of experience in the industrial coatings industry, he has specialized in rebar coatings for the past 8 years and currently holds the position of chairman of the Epoxy Interest Group. Mr. Del Percio holds dual degree from University of Phoenix in marketing and business management. He is currently involved in recent works at Texas A&M, Clemson University, University of Minnesota, and University of Illinois at Urbana-Champaign to develop and test innovative techniques to further improve performance to reinforcement steel products through coatings. So Anthony, I will turn it over to you now. Anthony, can you unmute your mic, please?
I can. I actually dropped off for a second.
Okay, yeah,
so I apologize for that.
Yeah, take your time.
Okay, can you see my screen now?
Yes, we can see your screen.
Okay. So good afternoon. First of all, I apologize, folks. I am traveling today, so I am not in the most quiet area. so I apologize for any background. Again, I want to say thank you to everybody that's involved here in the opportunity to present today. So we are presenting, and I want to take the time to thank everybody for joining us, during day 2 of the Tran-SET Corrosion Management System, Transportation Infrastructure for Long-Term Durability Reinforced Concrete Structures. It is kind of exciting here to be able to talk about new innovation. Obviously, if you look at the market and how we all work together, obviously Mike is on the galvanized side and I am on the epoxy side, and it's how do those two work together, and I get the opportunity to walk through that and some of the joint work that we've done with Texas A&M as well. So galvanized rebar with the additional layer of epoxy coating provides a significant advancement for corrosion protection and durability for reinforcing steel and concrete. So today I will discuss the innovative work happening with the ASTM A1055. So some background regarding Sherwin-Williams and our role in the rebar market. So Valspar had been supplying fusion bonded epoxy powder and epoxy touch-up liquid into the rebar market since 1993. In July of 2017, Sherwin-Williams acquired the Valspar Corporation. Likewise, Sherwin-Williams had been a long-term powder and liquid supplier into the industrial market. The combination of the two organizations gives Sherwin-Williams a unique perspective as a complete supplier in the construction infrastructure markets. The reason behind that is we have a vast group that works with bridge and highway, so we really do understand the infrastructure market from a DOT perspective and what innovations are needed to continue moving forward. So Sherwin-Williams is the largest coatings manufacturer in the world. Sherwin-Williams supplies coatings to over 120 countries with 91 manufacturing facilities, 60,000 people, and nearly 5,000 distribution points. So we not only look at this technology for North America, but for also as a global play as well. So at Sherwin-Williams, we work with all levels within the reinforcing steel supply chain. We work with the DOTs to provide technical updates and gain listing on their qualified products list. And once a product is listed with the DOT, we work with the contractors and installers to provide resources for the handling and access to the approved products. Additionally, we have relationships with several of the mills, applicators, and fabricators to ensure that the products they are using meet the specified requirements and perform to the level which provides benefits for them. Our goal is to provide performance products that have value seamlessly through the supply chain. And again, with this A1055 type product that we're working with CMC on and Texas A&M, this is going to fit right into the supply chain. So anything we bring in, we want to make sure it's seamless to the supply chain through to the end user. So ASTM A1094 is the standard specification for zinc coated steel bars and concrete reinforced, hot dip concrete reinforcing. So again, what do you get here? You get continuous galvanized process, which yields consistent formable zinc coating. It's a thicker pure zinc coating, as Mike mentioned earlier, which increases the corrosion initiation threshold. And it's better for bending and fabricating with no special equipment. So it really is an advancement from where galvanizing was prior. And then let's take a look at the A775, which is the standard for epoxy coated steel reinforcing bars. So epoxy coating reinforcing steel was first used in a bridge in the US in 1973 in Pennsylvania. In 1981, the ASTM A775 specification was created. And 10 years later, CRSI developed their certification program to hold suppliers to a higher standard. Epoxy coating provides a consistent, formable film coating. Epoxy coating is also a barrier coating which provides excellent corrosion resistance. And epoxy supplied is easily available through multiple coaters within the supply chain. So again, we're taking the existing supply chain that we have, and we're trying to figure out how to bring a better superior performing product to the marketplace through that existing supply chain. Now let's take a look at A1055, which is the standard specification for zinc and epoxy dual coat steel reinforcing bars. So the purpose of combining the CGR significant jump in corrosion resistance performance. A significant amount of research has gone into the development of this system, being that the initial challenge of the system is its ability to meet the flexibility of ASTM A1055 specification, independent of when the fabrication takes place after coating. So we worked very closely with CMC during the development and testing of the system to validate the performance of the system for the physical properties. So going a step further, we looked at how can we create a system that actually meets the flexibility of A775, which is more stringent than the 1055, which we have done. And here's a little bit into it. So during the development of the system, we looked at several passivation levels and modifications to the epoxy powder. As with any development we do at Sherwin-Williams, once we were able to meet the specified requirements, that's the 1055, we decided to push the technology to exceed the specification requirements, which would be 775. So these pictures show the flexibility of the system when tested to the ASTM A775 specification requirements, which are more severe again than 1055. Additionally, when developing an epoxy coating at Sherwin-Williams, we always test the coating at -30 degrees Celsius to -45 degrees Celsius, even though that coating will never see that temperature at fabrication. So in addition, what we're looking for is a high performance product to test for 100+ years life cycle. This gives us that superior performing product that competes with the other superior performing products that are in the marketplace right now. We want to exhibit superior adhesion over the continuous galvanized rebar compared to other powder technologies, make it cost effective, and then obviously we continue to collaborate with the DOTs and Texas A&M for independent evaluation. So let's go into the testing that obviously if you were on the call yesterday and on the call today, you've seen some of these 55. So here again, let's take a look at the electrical impedance testing. In this slide, we compare the ASTM 625 control material to the ASTM A1055. High impedance values due to excellent barrier protection coming from the epoxy. However, impedance decreased over time as a result of water penetration and initiation of corrosion process. The process is at the carbon steel substrate, which is a presence of a second time constant after 10 days of immersions. So as you see from the pictures, there's no visual damage to the 1055 system, which showcases its resilience. And then let's take a look at the 1055 protection model with long term. So as we look at this model, it's describing the benefit of the system utilizing the continuous galvanized rebar coated with fusion bonded epoxy. Again, Mike walked through this earlier today, and so we'll kind of walk through it here with the 1055. So of interest on this slide is the various stages of the corrosion resistance. In stage 1 and 2, there's no corrosion taking place. In stage 3, we see corrosion taking place. As the epoxy is a barrier coat, the barrier coat would need to be damaged prior to corrosion taking place. So again, no damage, no corrosion, but if you do happen to get damaged, you will start seeing some spot corrosion. And in stage 4, you can see the corrosion getting into the galvanized layer. Well, the zinc in this layer will sacrifice itself to extend the life cycle of the bar underneath. So again, we're getting the corrosion resistance of the barrier coat, but if we do have a break in that barrier coat, now we have the galvanized or the zinc layer to take us home to a longer life cycle. So for those who are familiar with the old Z-bar technology, this system performs similarly in theory. However, the zinc layer is thicker and less porous and has better formability. And additionally, this system can be provided by multiple suppliers to the end customer, which obviously would be the DOTs. So again, continuous immersion test. Mike kind of showed this before with his. We'll walk through this with the 1055. As we look at the continuous immersion results of this slide, we see that there's not a lot going on here after 30 days. This data shows the barrier coat, which is the epoxy, is still intact. As mentioned in the previous slide, as long as the barrier coating is not damaged, there will not be a corrosion point. As an update to this slide, testing past 1 year shows there is still not a lot going on as the epoxy coating is still intact. So let's take a look at the Cyclic Fog Chamber Test without damage. Again, in this slide, we look at the system. The blue is the oxygen in the salts. The green represents the zinc layer, and the red depicts the iron. And as you can see, without damage, the system is performing at a superior level. The barrier coat is still intact, and there's absolutely no corrosion taking place. And we move forward when you actually do the damage chamber test with damage. Area, which means we have really good adhesion and there's no undercutting of the coating layer. This system is performing as designed. That's why you have the epoxy and the zinc when damaged in the presence of a corrosive environment. So again, there's things that are being discussed with different states. So I don't have a lot of case studies here like Mike does with the Galvabar, but we know there's interest in New York, in Florida, South Dakota, Texas, Louisiana, for this type of technology. So in conclusion, let's take a look at the summary of the points highlighted, highlighting the value of the epoxy over CGR. So one, it's a highly innovative product that raises the performance bar to new standards. Internal results show significant corrosion enhancements from epoxy over CGR. There's an enhanced barrier resistance from an added layer of epoxy coating. A Sherwin-Williams powder product shows superior adhesion and flexibility over CGR compared to the existing powder technologies. The compiled results so far indicate a cost-effective coating for high-performance applications with potential to replace stainless steel bars. And independent evaluation results are still forthcoming from Texas A&M. And again, there's interest from several DOTs to evaluate this system. So with that, that's the end of my presentation on the 1055 innovation.
Okay, thank you very much, Anthony. That was excellent. Really appreciate it. So now I will introduce our last presenter, Dr. Salim Faza. Dr. Faza is responsible for expanding high strength and corrosion resistance products and technology in the concrete reinforcing industry. His contributions in engineering include leading the development and acceptance of the ASTM reinforcing bar specification for high strength steel, ASTM A1035. Currently, Dr. Faza is coordinating code development for concrete designs with high strength steel rebar. During Dr. Faza's more than 30 years of experience in the concrete industry, he has specialized in conventional and advanced reinforcing products, and he has been involved in the development and code acceptance of advanced reinforcing products nationally and internationally. He has planned, supervised, and coordinated all phases of application engineering, including research programs at more than 20 institutions worldwide. Dr. Faza holds a PhD from West Virginia University in Advanced Composite Applications in Construction with an emphasis on rebar for concrete application design and analysis. Dr. Faza currently chairs the ASTM A1035 subcommittee and the ACI 439 subcommittee on design guide of high-strength rebars ASTM A1035. Dr. Salim, I will turn it over to you now.
Thank you so much for the kind introduction, and thanks everybody for attending the webinar today. Let me try to get where I want to be. Okay, you see my screen and you hear me well?
Yeah, everything is good.
Perfect, perfect. Well, thank you for the introduction, and thank you for being here today to allow me to introduce you to the mechanistic performance of the continuously galvanized high-strength corrosion-resistant Chromex reinforcement. So based on yesterday's presentations and this morning presentations, we're continuing to advance the technologies and looking at ways to provide new products with different technologies. So before we get into anything else, I want to brief you on what is Chromex. It used to be called MMFX 20 years ago, and it is a reinforcing bar that has a different kind of microstructure and different chemistry, and that's how we distinguish the material characteristics of the Chromex material from regular carbon steel. So Chromex basically complies with ASTM 1055, depending on the chemistry of the product. In this instance, you have Chromex 9000 series. It has a minimum of 9.2% chromium content. It's available in both 100 KSI and 120 KSI. So we designate it as an ASTM 1035 CS. Typically is used in applications where you have severe corrosion environment caused by either seawater or the icing salts, and it exceeds the 100-year service life for infrastructure projects. The second type that is offered is the Chromex 4000 series. It is designated as an ASTM 1035 CM, and it provides a mid-level corrosion for over 60-year service life, depending on the type of structure that you have. Also, we have a third type, but this type is a made-to-order product. It's not available in stock. It is purely for high-strength applications. It might provide you with some corrosion resistance, but it is a product that's Chromex 2000 series, which is designated as ASTM 1035 CL. Now, as I mentioned to you, the product looks like a regular steel product. It has the same deformation pattern. The only thing different about it to start with is the chemistry. So how do we make this product? The product first is produced in billets, just like any other steel. Now, during the melting process of the steel, we're able to achieve a certain chemistry that are required by our production process, as well as by the minimum requirements and maximum requirements per ASTM. So we control the chemistry and we add the amounts of chromium that are required, and we reduce the carbon within that chemistry mixture. After the billets are produced, then we go into the rolling process. Now, in the rolling process, we control the temperatures or the cooling parameters of the steel, and we're able to achieve a new microstructure. So once we achieve the chemistry through the melting, and once we control the temperature cooling parameters, we're able to achieve a new microstructure of the steel. And you can see here it is, this is a high electron picture of the microstructure. It's made out of martensite and austenite. Now this is the major difference between regular steel and the chromic steel. Regular steel is called pearlitic steel. It's made out of ferrites and carbides, and that is the problem when you have the chlorides and you have the oxygen and the water, you get a batter-like effect that starts deteriorating the steel from the inside out. In this case, we have achieved a new microstructure that is made out of martensite and austenites and have minimal formations of carbides within the microstructure. And this microstructure allows the steel to be corrosion resistant and provides the high strength and ductility. So as anything else that we do, engineering wise, we have to abide by certain specifications, because when DOTs or engineers specify a product, they have to go by either the ASTM standard or the AASHTO standards. In this case, we go by the designation of A1055. It is the standard specification for low carbon chromium steel bars for reinforcement. As you will see here, it has 3 different types. You have the 1035CL and CM and CS. And as I mentioned to you before, we control the chemistry in according to the carbon and chromium content. So for the 1035CS, you have a 10 to 10, it's 8 to 10.9 chromium content with a 0.15 maximum carbon content. And for the 1035CM, you have a 4 to 7.9 chromium content with a maximum of 0.2% carbon. Now, even though the ASTM composition allows us to go between 8 to 10.9, but when the rebars were tested in accordance to the AASHTO specifications, all the bars that were tested had a minimum percentage of 9.2% chrome. Therefore, all our productions are required to have a minimum of 9.2% chrome as per the AASHTO standards. So as structural engineers, this is a very unique product because it gives you both the corrosion and the strength. We are typically used to grade 60, and we advance the technology to grade 75 and grade 80, and now everybody's talking about 100 KSI products. 100 KSI products are produced for relief of congestions, for reducing the quantities of steel within the structure. As you can see here, we're comparing the different ASTM A615 grade 60, 80, and grade 100 versus grade 100 A1035. All the different types of chromics products under the ASTM 835 designation have the same mechanical properties. So even though you have differences in chemistries in terms of the chromium and carbon content, we're able to achieve the minimum yield strength of 100 KSI, minimum tensile strength of 150 KSI with minimum elongation of 7%. Now, the beauty of our product is that it produces a product with a minimum actual tensile to yield ratio of 1.25 versus 1.1 for the A615 grade 100. And you can see here the typical stress strain characteristics of all the different bars. The black one here is the A1035, and it shows the roundhouse curve without any defined yield point. That's why the yield strength is defined by the 0.2% offset. Now, understanding that these properties are available for people to use their designs up to 100 KSI, the AASHTO LRFD, as well as the ACI 318 19 code allows the use of the products up to 100 KSI in design. But we have the design guidelines available that would allow us to use them either on a 1-for-1 replacement or using it at a design where we reduce the bar diameter, gives you the opportunity to design the structure with about 80 to 85 KSI, or you can utilize the strength, the full strength of the rebar according to the design codes that are available. This is the AASHTO M334. The AASHTO M334 is a standard specification for the uncoated corrosion-resistant chromium alloyed steels. So what does that mean? It has all the chromium-bearing steels that are uncoated that are labeled as corrosion resistance. And you see here all the austenitic stainless steels, the duplex stainless steel, and the 1035 CS that is available. And that's where we're restricted to a minimum of 9.2% of chromium in the steel, as I mentioned before. That's why we only produce the steels with that kind of chemistry. Now, another thing, just like GalvaBar and what Mike mentioned to you, in our case, back in October 2017, we used to be called MMFX Technologies, and it was acquired by Commercial Metals Company and integrated the product into their global steel business. As Mike mentioned, CMC is a global company that has metal recycling, steel production, steel fabrication, and installation in some parts of the United States. However, we pride ourselves as Commercial Metals by introducing to the market an array of products, whether it is for strength and ductility and toughness or corrosion resistance. In terms of the strength, ductility, and toughness, we're the first company that produced spool bars in the United States. We produce high strength steels like the A615. We produce the chromic steel, which is the A1055, and we produce very unique product that's called cryo steel that is used for low cold temperatures such as LNG tanks. Now, in terms of the corrosion resistance, some of these products we produce ourselves, and some of these products we'll only touch them for the fabrication or the installation. So we're one of the largest green epoxy coating facilities in the US. We work with hot dip galvanized. We're the producers of GalvaBar, which is the A1094, and the Chromex corrosion resistant bar is 1035, and we sometimes work with the stainless steel when the job requires the stainless steel. We do this throughout the United States with about 10 melt shops. We produce over 8 million tons capacity. And the chromic steel comes from two places. It comes from either the South Carolina facility, which is a Commercial Metals facilities, or it comes from an independent facility for the West Coast, which is available through Cascade Steel in Oregon. We also produce 150 KSI all-thread bar that's available with the chemistry of the Chromex material that's available from South Carolina. And you see here the GalvaBar from Oklahoma, and the cryo steel comes from Mesa, Arizona. But you see all these dots show the fabrication and the melt shops that we have throughout the United States. So we're talking about corrosion, and we're talking about technologies that provide concrete durability at economic cost, as every DOD and every owner looks for a product that would give them the ability to design structures that will give them the best service life for the amount of money that they want to spend. But over the past 20 plus years, everybody's been ranking the products according to what we call the chloride threshold. Chloride threshold is a value that is typically used in modeling of structures. So based on the models that you have from black bar through epoxy, through hot dip galvanized, through Chromex, and 1035 CM and CS, we're able to take these values and in accordance with where the bridge project is, depending on the location, depending on the weather, the temperatures, the concrete mix design, the cover, all this will go into modeling to predict when is the first repair is expected for the bridge. And depending on the type of material, we can come up with a time to corrosion initiation based on the theoretical values that we do through accelerated testing. So these are theoretical model, but recently we advanced this technology and we started ranking them and comparing them for the service life. So looking at the Chromex 4100, we've already established the chloride threshold and corrosion rate. We even have coated the Chromex 4100 with epoxy coating in accordance with A775 requirements. And by doing so, we were able to achieve 109 years with a epoxy coated Chromex 4100 versus a conventional epoxy coated that was 58 years. We've established that Chromex 9100 can be used for 100 plus service life, and we've established that the 4100 can give you the 60 plus service life. However, as a structural engineer, we're always wanting to understand how can we improve on the structure, especially in serviceability issues. Now, what do I mean by the serviceability issues? As I told you before, everybody's looking at, okay, well, how long does it last? When do we start repairing it, etc. But when you're using a material that corrodes, every material corrodes, whether it is a stainless steel or whether it is a galvanized steel or whether it is a chromic steel or epoxy coated steel, everything corrodes. So what people are looking right now is how does the corrosion through the service life of the structure affect the serviceability of our materials. Now, in this case, we have lots of studies that have been conducted on comparing corrosion-resistant rebars, and the most things that we will show that the Chromex 9100 rebar shows the superiority in terms of corrosion resistance when it applies to the cracking, the bond strength, and deflection and ultimate capacity. All these were looked into to be able to give you what kind of serviceability issues that you expect to have. So the independent tests that have been showing the serviceability issues for the Chromex material over stainless steel and other product is what happens when rebar starts cracking. So they've tested structures that are reinforced with different materials and subjected them to environmental conditions as well as loading at the same time through either simulated thermal chambers or actual thermal chambers, where they looked at the bond losses, they looked at the cracking, and they looked at the deflection and the moment capacity. And it has been shown that using the Chromex 9100 has a homogeneous effect and behavior through its bond strength on the overall concrete bar system. So now, instead of just talking about the corrosion resistance of a bar, we're talking about the concrete bar system behavior and performance as it relates to stainless steel and other corrosion resistant bars. So the product that we're talking about has been used and accepted and implemented since 2002. This is a map of North America, wherein you see the places and the states and provinces that Chromex has been used in the past, and the table shows you some of the approvals and the pending approvals that we have from different DOTs throughout the United States and the provinces in Canada. The type of projects that we do, of course, over the past 20 years, we've used it in over 1,000 bridges. The unique thing about the product that people started using it on a one-for-one replacement in the early days until they got the confidence level that the product can provide them a solution for high congestion, and they can use it for advancements in design of bridges. To showcase the use of our material, we have the Lesnar Bridge replacement in Virginia Beach. It received the 2019 Bridge Awards of Excellence. The bridge totally was reinforced with Chromex 9100, but the beauty about this project that they utilized the higher strength and you used it throughout the structure at a grade 75 design. This is the Maryland Transportation Authority. This is the first bridge that is designed with A1055 CS, and the construction started in the spring in 2019, and it is opened ahead of the schedule. So I'm showcasing some of the state DOTs that have used the material and how happy they are. This is the Alaska DOT using the Chromex 4100 since 2019, and the contractor said that it's much easier and better handling than epoxy coated bars, and they've saved plenty of construction time. They don't worry about the nicking or cuts or repairing, and they encourage every DOT to use it everywhere. Washington State just started using the Chromex 9100, and this is the first project that they're utilizing it at 100 KSI design level. West Virginia Department of Highways started using the Chromex 4100 and Chromex 2100 throughout the structure, and this is one of the first states that started the designs of the bridges at 100 KSI design strength in all the substructure and the superstructure of the bridge. Due to the corrosion resistance of the material, this is one of the largest diaphragm walls that were constructed in the state of Abu Dhabi, wherein they had a seawall that was originally designed with stainless steel. And due to the corrosion requirements for this bridge, for this diaphragm, it was very costly to build it with stainless steel. So the designers looked into replacement of the stainless steel with the Chromex 9100. They designed it at a 90 KSI level, and the reason why, because they were doing it in accordance to the Eurocode. The Eurocode only allows them to go up to 90 KSI. And you see here, this is the diaphragm wall that's about 70 feet deep, and the facade is made out of the Chromex material, and it is immersed into the seawater. So bringing us here to what we've been talking over the past 2 days about the continuously galvanizing of the Chromex corrosion resistant material for exposed applications. As you've been hearing over the past day of today and yesterday, we are looking into advancing the technology of continuous galvanizing and how that affects the designs of our structures. The reason why we're looking for galvanization of the Chromex is for using the Chromex or galvanized Chromex in exposed applications. We are looking into continuous, first of all, the continuous galvanizing process does not affect the microstructure or the mechanical properties of the rebars. We've tested the bars after and before, galvanizing them through the process, and the material properties and the microstructure has not been affected, and actually the A1055 has been added to the specification of 1094, so it is allowed to coat it without sacrificing any of the microstructure or the mechanical properties. We're looking into expanding the product applications, wherein we can use the product in marine applications where they're exposed to the different environments, where applications are currently only specified stainless steel in splash zones and all the things that it's expected to be highly corrosive areas. we're looking into extending the service life in severe corrosion environments. And we're also looking to use this process of continuous galvanized process on the old thread bar that's produced by commercial metals, made out of the Chromex technologies in terms of the chemistry. So this is the equivalent to a threaded bar 722, but it's made out of the Chromex chemistry, and then it is continuously galvanized. These applications are good in piles, caissons, and some mining applications. So based on the presentations of yesterday from Dr. Homero, and based on what Mike presented to you today, I'm not introducing anything new to what you've seen already. So this is the process of corrosion protection using the A1055 coated with the galvanized for long-term exposed applications. We're still very early in the stage and the testing right now in terms of our material. By looking at, just see what's happening, you have a diffusion of the aggressive materials like the chloride and the oxygen and the water. These are the catalysts that will start the corrosion. So it takes time for it to penetrate through the concrete, and that is what we're calling the diffusion process. And then followed by the diffusion process, you're going to reach the sacrificial and barrier protection period, wherein the corrosion products of the zinc starts being utilized. So it gets diffused through the concrete, and then once it reaches the protective layer of the zinc or touches the zinc layer, it starts dissolving the zinc layer, and that is where it starts activating that corrosion process. All this still has not reached the level of the Chromex steel. So all the data that we currently have, we're still in the stages, we're still at the zinc corrosion products formations. So similarly here, we show you the continuous immersion test. In this test, of course, as Dr. Mero mentioned yesterday, we skip the diffusion process and we immediately go into the solution, wherein you avoid, you just go to the corrosion rate basically. So the zinc is the sacrificing, protecting the steel and forming a very uniform corrosive product. And we still have not reached the steel layer. And as you can see here from the data that was presented today and yesterday, the material of the Chromex still has not been activated. In this case here, you already have a steel already corroding and eventually cracking the concrete and spoiling the concrete. But in the case of the 1035 with 1094, we're still at a stage wherein we're showing only the zinc material activation. Both products are being tested. The 1035 CM, which is the 4% chrome, and the 1035 CS, which is the 9% chrome. Both of them have been continuously galvanized, and as you can see, no activity is happening here for both products because we're still at the stage where has not depleted all the uniform zinc layer that is on top of the product. So we'll keep on looking forward to get to that point where we will see something going through to the steel and show the corrosion resistance of the steel, how it affects the longevity of the 1094, 1035 product. And with that conclusion, I thank you for your attention. And we have built structures throughout the world for all types of corrosion resistance and high strength, whether it is in marinas or bridges or ferry terminals or piers, foundations, architectural precast, seawalls, highways, and bridges. So we keep looking forward to working with all of you in the near future and eagerly awaiting the results to come out to show the application of the Chromex with the continuous galvanization. Thank you.
Thank you, Dr. Salam. We really appreciate your presentation. So this concludes the presentation portion of our webinar, and now we will start receiving questions from the attendees. So you can just type your question in the chat box or in the Q&A box. And again, if any of the attendees would love to share the discussion, he can use the raise hand option, and I would allow him to talk. So I can see our first question to Anthony Del Percio. So the question is, green and purple epoxy are used for existing coated black steel products. Yellow was used for Rebar, which was specifically epoxy over thermal sprayed zinc. A new color is needed to differentiate epoxy over galvanized zinc. How about blue?
Yeah, right now we have not looked at changing the color with the testing that we're doing. So it has stayed green. If we were to continue to move forward and there was a question from the DOT regarding, what that color, they would want a different color, changing the color would not affect the overall performance of the product.
Okay, thank you very much. So there was a common question in yesterday's presentations, and I think that all the presenters, they gave very good answers for that from different perspectives. But I would also to hear your point of view regarding this, about the impact of these different rebars on the service life or the improvement in the infrastructure. So how does these different materials, as related to the control rebars, how do they improve or enhance the service life of the different infrastructure?
Well, excuse me. I'll speak for galvanized coatings. With whether you're choosing A767 or A1094, there's already a long case history of back into the 30s and even 50s when it was federally specified for projects out there. A1094 just represents an improvement in technology and advancements for developing more efficient use of the zinc. So it's expanding upon that. And then we're being used as a base for the 1055 product for epoxy, and then as a coating for Chromex. And Salem and Anthony can speak up, but it's an extension of that. Really, the competition out there in the marketplace is stainless steel at a very, very expensive cost. And I think both these applications are going to be providing opportunities for longer life at reduced costs. And I'm talking about longer life beyond 100 years.
Great. Definitely, we're all our products. We're products that lend its technologies to extend the service life at the lowest cost that is possible. So it depends what kind of service life you're looking for and what are the products that will be able to provide you. So, Commercial Metals offers you all the different products from the GalvaBar to the Chromex, 4100, Chromex 9100, and even epoxy coated rebar and epoxy coated Chromex and galvanizing Chromex. So depending on the type of product that you're looking for and the service life, you will see a big impact into how these materials would give you over the service life of the structure.
Yeah, and I would just echo that as well. Anything that we're doing in the marketplace it's all about driving innovation, and right now the innovation is being driven towards improved life cycles and getting to that 100-year bridge they're calling for. And so even on the epoxy side, we're looking at different technologies and different ways of doing things to improve our corrosion resistance, our barrier properties, and then obviously going over some of these other corrosion-resistant type substrates, you can get some sort of advantage from both of the systems being used together.
Okay, thank you very much. So I can see Gary Dallin who wished to participate in this discussion. So Gary, do you wish to participate?
Yes, please.
Okay, can you just introduce yourself quickly?
Gary Dallin, I'm the director of the Galv Info Center, which is a program of the International Zinc Association. And I was involved in the development of A1094 5 years ago. I have a question for Salem about A1035. Salem, the corrosion products of A1035, when they start to develop, are they as voluminous as on plain rebar A615? Or are they
no, they are not. They are much smaller in volume compared with that of the regular normal steel. And that has been shown in research conducted, and I do believe that the volume is going to be about, I mean, I've got to verify that, but I think it's about 1/3 the volume of the oxides that come out from A615.
Okay, I was wondering because it's probably the effect of the chromium in there that keeps those down.
Absolutely. And of course, you've got to have the microstructure of our steel, which is the one that controls the corrosion resistance, and with the minimal amounts of deformation of the carbides, all of these are factors that would result in a better performance than the A615 in terms of corrosion.
Okay, thank you. One more question about the mechanical testing of all the A1035 products. When you are measuring the yield strength, is that all based on 0.2% offset?
Yes, because as you know, the bars, as I showed you from the stress strain characteristics, all the bars have a roundhouse curve. Yes. And the only way that you can identify what would be the yield strength is by the 0.2% offset. And this is in accordance accepted by all the design codes and the specifications.
The reason I asked, Salem, was I noticed on a couple of the curves, they appeared to have a bit of a drop of the beam there with a
those were the grade 60, 80, and 100 of A615.
Oh, that's right. Okay, thanks.
Yeah, I only had one curve for the Chromex material, which was when you see the presentation, it's the black line, which was the top that has the roundhouse curve. The rest of them were A615 grade 60, 80, and 100.
So on the A615, they're still, the yield point is still determined by the offset, or
no? I mean, you're allowed to do both, but in most cases, all the grade 100 bars that I've seen so far have a well-defined yield point for the A615.
Okay, so that's the measurement. Okay, thank you.
Yes, sure.
Okay, great. So our next question is in the chat box. I'll read it. What are the cost differences between the galvanized bar epoxy coated only or dual coated? I'm guessing the Chromex is more costly than those others.
I'll take a shot at this. For the pricing, mostly we're looking at when we're looking at galvanizing the Chromex technology, we're looking at the 4100, and for the dual coat of the epoxy over CGR, we're looking at just standard A615 or A706. And with both of those, you're going to end up with a pretty similar cost. You know, galvanized coatings are relatively inexpensive compared to stainless steel, but you're going to get a little bit of an addition, as they say what the market will price it at. But Z-Bar was competitively priced around $1.25 in that range. So you're probably looking at, including bar, you're probably looking at under that range or comparable, just to take a quick guess.
In terms of the Chromex bars, you know, we have both products. The Chromex 9100 is typically compared with the stainless steel applications. Therefore, when you have a bridge design that's required the 100+ service life, typically you'll see a stainless steel or a Chromex 9100, and it is much lower cost than the stainless steel. If we're talking about the Chromex 4100 standalone, the product is typically used against, for 60 plus 75-year service lives with either epoxy coated bar or hot dip galvanized. And when you take advantage of the strength of the product by designing it up to 80 KSI, you will be able to offset any extra costs that is available. And that's how we typically look for the product, is utilize both the strength and the corrosion resistance of the material. Now, as Mike mentioned, he talked about the Chromex being galvanized.
Okay, thank you. So the next question is, what is the reason of getting magnetized of Chromex rebar due to cutting or drilling? Will it change the corrosion performance of rebar? So this is one question, and the other question from the same attendee is, what is the reason of galvanizing Chromex rebar if they have a corrosion resistance comparable to stainless steel?
Okay, so definitely I have the answer for you. I don't think that the bars are magnetic bars, right? So we do only cut the bars. We don't torch cut the bars. I don't know what is meant by what is the reason of getting magnetized of Chromex rebar. But anyway, I will try to answer the rest of the question. The corrosion performance of the rebar does not change through the cutting or the drilling, because you're not changing the microstructure of the steel, and you're not doing anything to the performance of the steel. In terms of the reason for galvanizing Chromex rebar, as I mentioned in my presentation, we're looking to expand the market to places where there is a direct exposure to the chlorides, like the all-threaded bars. All-threaded bars are typically, will have some kind of exposure to the chlorides directly to the bar. That's why the galvanized, the continuous galvanization on the all-thread bar would be perfect, because it will protect the surface of the rebar from that environment. And we're also looking for applications where it is highly corrosive applications, wherein there's a direct contact with the salts or with the soils. And that's where we are coming up into the market with the galvanized Chromex rebar. We're still in concrete applications. We have both the Chromex 4100 without any coating, and the Chromex 9100 are doing the work for these kind of bridge applications where we don't need the coatings on them.
Okay, thank you very much, Dr. Salim, for your comprehensive answer.
Sure.
So I think this
There's one more question. It says, in your opinion, what's the difference between studies that shows ECR has better corrosion performance compared to Chromex and studies that I've summarized? Is there a problem or the weakness in the study? Well, listen, when you are comparing Chromex is an uncoated product. The Chromex material is like you can test it like black steel, you can test it like stainless steel. When you are comparing it with the epoxy coating, you have a problem, is that the epoxy coating is a coating. So you're not testing one versus the other in the right way. That's one thing. It's like apples and oranges. So you're always going to have a difference, because all the testing that is done on the epoxy coating take into account that there is a hole, that there is a damage. It's true. But when they measure the corrosion potentials and they do all these things, they take into account that only that part of the surface, which is the drilled hole, is the one that's been exposed to the environment. And if you look at the chloride threshold of the materials, you will notice that it is better for the Chromex. So when you're talking about chloride threshold for Chromex material, that is The 9100 is about 2,000 parts per million. The chloride threshold of the 4100 is about 1,600 parts per million, and the chloride threshold for epoxy coated bar is about 900 parts per million. And the corrosion rate of the epoxy coated rebar is typically same as they would have it for a black steel, because once the rebar gets corroding, it accelerates under the surface condition. So unfortunately, there is no single test that can apply to everything, because it's either you're testing a coated material or you're testing an uncoated material.
Okay, thank you, Dr. Saran. So
Thank you.
before concluding our Q&A session, I can see many positive comments in the chat box. So one of them is thank you to all of the presenters. I learned a lot. Another one is excellent presentations. GalvaBar and Chromax are great product for the bridges. So again, we would like to thank the attendees and the presenters. So again, I would like to thank the three presenters as well as the attendees. And please let me know if you have any questions about the webinar series and about Tran-SET. Otherwise, have a great rest of your day. Thank you all.
Thank you, Dr. Musa.
Thank you.
Thank you.
Thank you.